Question 12. So what am I being asked to do? So show that the x-coordinate of the turning points of the curve for this equation, satisfy the equation tan x equals 4. So I want to know the x part of this, so that means I need to differentiate and find out when that's equal to 0. So differentiate this just here, and that's product rule. All right? It's got something multiplied by something, product rule. So remember, we get y equals uv. How do you do that? Remember, it's going to be u dv plus v du. Okay, just best thing to do is just to write everything down. We've got u and we've got v. Let's just jot these things down. And we've got du. Well, we haven't got du yet. And dv, right? So u is 10e minus 0.25x, and v is sine x. So I'll do the easy one first, cos x. Right, this one here, if I differentiate that, I know I'm jumping a little bit here, but you can work at your differentiation there. And 25x, there you go. You can just use a bit of chain rule there if you're not sure, okay? Okay, let's piece all this together and just put it into this form here. So I've got, what's that going to give us? So for dy over dx, I'm just going to write it down here. Obviously, I'll be doing this on a separate page, okay? I want you to be able to see it all. So that's going to be, we've got u dv, so let's just write that down, 10e to minus 0.25x cos x, and then plus, and then v du. So these two just hit. Oh, it's going to be a minus, isn't it? Because I've got a minus there. 2.5e to the minus 0.25x. And we're going to multiply that by, squeeze it in there, cos x. So, whoops, made a mistake, haven't I? That should be sine x there. Yeah, okay, because it's v du. All right. Careful on that sort of thing, because I kind of cheated and wrote it the other way around and nearly made a mistake. Okay, from here, we want to know when this is going to be equal to 0. Well, the easiest thing to do is let's factorize. And if we were to take out a factor of 2.5e to the 0.25x, I think that's probably the simplest way of doing this. So 2.5e minus 2.5x, what's going to be left inside? I can have 4 cos x minus sine x, and I'm interested in when that's going to be equal to 0. Right, well, this here, that's not going to equal 0 because of this e part here. Right, when's this going to be equal to 0? That's the other one to consider. Well, that would be 4 cos x, imagine adding sine x to both sides, equals sine x divided by cos. So 4 equals sine x over cos x, which is tan x equals 4. Okay, that's where we wanted to get to. So there's part A done. Right, part B. Part B is nice and easy because it says sketch the graph. Well, look, we've already got this here. And all we need to do is sketch the graph, the modulus of this. So all that means, and I'd probably just do this on the same graph, I think, is that rather than these bits coming down here, they're just going to come up like this. So it's the same graph, and it's just going to be above the line. Okay? So just make that really clear. You can always sketch it out again. Right. Then part C. So part C says, using a model, the maximum height of the ball above the ground between the first and the second bounces. So you've got a ball, it's bounced, there's the first bounce, there's the second bounce. So we're actually interested in what that value is just there. So in order to get that, we need to know what this point is here. Now remember, we've just worked out this tan x equals 4. So if we simply arc tan 4, we get 1.3258. All right, so that's this value just here. Obviously, there's a little bit more to that. And then the period of tan is pi. It's like plus 180, isn't it? But remember, we're working in radians. So this value here is 1.3258 plus pi. So that's going to give you 4.467 and a little bit more there. Okay. So all we need to do is we just need to sub this value into here. And if we sub that in, that's going to give us, now obviously if you just put it into here, it's going to give you a negative value. But we're going to take the positive answer to that. So if we just sub it in, and it gives us 3.18 meters. And then, so we've done C. Now part D. Explain why this model should be not used to predict the time of each bounce. Well, if you think about what's going to happen when a ball's bouncing, is that this model is suggesting that the time between the bounces is constant. Well, in reality, this is going to be closer as the bounce gets less. You would imagine that this is going to become less. So we need to be quite careful about that. So the kind of answer that we need to write down is that the time between bounces will reduce. This model suggests that it's constant. There you are.